So I'm Alon Faktor, and this is joint work with Michal Irani, video segmentation by non-local consensus law. So what is the problem we're trying to solve? Given a video sequence, our goal is to segment the video into the foreground moving objects and the background. And we want to do this even for very challenging unconstrained video sequences, such as videos with severe motion blur, non-rigid background motion, non-rigid foreground motion, and complex 3D parallax. Now, video segmentation has been widely addressed in the visual community. I will now just briefly mention the most popular and recent methods. The first family of methods are trajectory-based methods. This segments the video by clustering motion trajectories. However, since it is very hard to track a point for too long, the resulting trajectories may be quite short. And this causes all kinds of segmentation errors, as can be seen in this video over here. For example, in this frame, the woman is merged with a large portion of the background, while her arm is segmented as a different cluster. The second family of methods are supervoxel-based methods. These start with space-time over-segmentation of the video and proceed by merging regions using local space-time similarity. However, it is very hard to decide where to stop, and therefore you cannot avoid over or under-segmenting the video. This can be seen in this example over here, and we see that there still remains a large amount of over-segmentation in this video. The third family of methods are graph-based methods, and these are the current state of the art for foreground-background video segmentation. So in the current graph-based methods, each pixel or superpixel is associated with a foreground-background node. Information is then propagated to neighboring pixels and neighboring frames based on optical flow. And then, in order to get a binary segmentation, usually an algorithm like GraphScat is applied. Now, there are two problems with this approach. The first is that foreground background initializations tend to be very noisy, especially for challenging unconstrained video sequences. For example, we can look at this video, and here's an example of such an initialization where red signifies high likelihood of being foreground and gray, high likelihood of being background. And you can see how noisy this initialization is. Now, that by itself may not have been such of a problem had optical flow been accurate enough. However, optical flow is also very noisy, which means that in practice, the propagation of information is done only locally in time. And the reason for that is that optical flow errors rapidly accumulate, thus inducing very low weights, often zero weights, between related parts of faraway frames. Therefore, current graph-based methods cannot recover from such erroneous and noisy initializations. And this is what would happen if we try to use this initialization and current graph-based methods. This is the segmentation result you would get. And you can see, of course, that it's very inconsistent over time, and it misses large parts of the girl here, and also assigns large portions of the background as foreground. So this is really a bad segmentation. So in conclusion, current state-of-the-art methods do not handle well video sequences which are challenging and have non-rigid motions, severe motion blur, and low-quality video. And this is what we want to handle in this work. So let me first give you a high-level overview of our approach. Our approach is also graph-based. However, unlike all the previous methods where the information was propagated only locally in time, our propagation is highly non-local. And the non-locality is both in space and in time. So what do I mean by that? What do I mean by non-local? So let's take a look at the following video. And here is this region over here, this red region, the leg of the girl. So well, we can find a very similar region to that, also in a very far away frame here, like this red region. Well, these two regions are very similar, so we'd like to propagate information between them. And if we try to do this using optical flow, it would not work, because optical flow would just not get that far. Instead, if we would alternatively look for similar regions based on appearance properties, then we would be able to find these two regions and connect them as neighboring nodes in our graph. So this is what I mean when I say non-local, and actually want to do this for many, many, many regions across the entire video sequence. So here's just another example, this green region, the head of the girl. So of course we can find it at many other frames across the video. Okay, so like all the other approaches, we also start from very noisy initial foreground background roads. And again, we see an example. So we can see, for example, that at this frame, we get a pretty good initialization. Most of the girl is in red, and only little portions of the background are marked, have high likelihood of being foreground. But there are other frames, like the middle one, that the girl is not marked at all. So there is here a large amount of noise, and the initialization seems really bad, and it seems that you could not recover from such a large amount of noise. However, what I hope to show you in this lecture is that using the non-local graph structure, both in space and in time, this will allow us to recover from such a large amount of noise, because what we will do is we will allow crosstalk between distant regions in the region, meaning that similar co-occurring regions which are distant in time can all reach together globally a consensus voting whether they all think if a pixel should be a foreground or a background. Now, of course, you can ask, why should this middle girl, this girl tell the other girl that she should be foreground and not the other way around? Well, this depends on how noisy the initial votes are to begin with. And it turns out that if at least 50% of the votes are correct to begin with, then you can actually recover the correct foreground background assignments. And we'll see an example of that. So here are the final foreground background assignments after the consensus voting, and we can see they correspond to a very good segmentation of the girl. We see that they sit almost only on the girl. Okay, so this was a high-level overview of our approach, and now let's get into the details. So the first step is to represent the video. So we do so by extracting many small regions, many superpixels, for each frame. Actually, we have here something like 1,000 or 2,000 superpixels. This appears to be quite a large number. And these small regions, small superpixels, will form the basis to our regions. The next step is to represent each and every one of those regions by a descriptor. So we use several types of descriptors. The first is a color histogram. The second is a Hogg descriptor computed around the center of the superpixel. And this may exceed the size of the superpixel, and it captures the local structure within the vicinity of the superpixel. Finally, we also incorporate the relative position of the center of the superpixel with respect to the currently estimated foreground object. And at the beginning, we don't have a good idea of what is the foreground object. It is just with respect to the center of the frame. But as we will go on, we'll see that this is an iterative process. Every several iterations, we can update this. So we are kind of trying to track the foreground object and move to the coordinate system of the moving object. Okay. So the next step, now that we have this, we've defined this feature space for all of these regions, the next step is to construct a graph. So what we do is that for each of these superpixels and its descriptor, we look for nearest neighbors in the feature space I just defined here. And we find nearest neighbors. And note that these nearest neighbors are close only in this feature space. So they can be very far away, both in space and in time. And this is actually what creates the non-local graph structure. Okay, so now that we have this graph, all we have to do is to somehow initialize the foreground likelihood votes. And I'll explain in a moment how we initialize them. So each node is a graph which corresponds to some superpixel in the video, gets its vote. And we can see that here all the different colors, where red signifies high likelihood, gray low likelihood. And then all we have to do is to perform the consensus voting. So what do I mean by consensus voting? So consensus voting is just a diffusion process where we replace the foreground likelihood vote of each node in the graph by the weighted average of the foreground likelihood votes of its nearest neighbors in the graph. So we just diffuse several iterations and get the final votes. Now again, assuming that the votes were not too noisy, meaning that at least 50% of the pixels had correct foreground background votes, this will create a very good separation between the foreground likelihood votes of the true background pixels and the true foreground pixels. And what you see here are two vote profiles of each of the background, the gray curve, and the foreground curve, the orange one. And we can see this in this video over here. And we can see that it is enough just to threshold the foreground likelihood values in order to get a very good segmentation of the curve. So unlike the other methods, we don't have to do any belief propagation, any graph cut. All we have to do is, after we do this diffusion, just put a threshold on the foreground likelihood. Okay, so the only detail left to tell you is how we initialize the foreground likelihood votes. So we'll use here a very simple and crude initialization, which is also very fast. So what we do is we just downscale each frame and compute coarse optical flow. And then for each frame, we'll ask check if it contains a dominant motion. And if it does contain a dominant motion, I'll explain in a moment what I mean by dominant motion. If it does contain a dominant motion, then we'll assume that this motion is due to background camera-induced motion. And therefore, we'll assign all the flow vectors, which are consistent with this dominant motion, to be background pixels. And all the flow vectors which are inconsistent with this dominant motion, like the yellow ones, we'll give them a high value and assign them to be foreground. Now, there are cases where we are not able to find any dominant motion. So in that case, we'll consider this frame to be unreliable for initialization and just blindly set the foreground votes to be 0. So what do I mean by dominant motion? So here we have two cases. The first is to look at the optical flow magnitude and check if there is a strong peak around 0. And if there is a strong peak around 0, then this corresponds to 0 motion, meaning that the camera was static or nearly static. So all the pixels which have low optical flow magnitude will be background, and all the ones that have high magnitude will be foreground. The second case is to look at the optical flow orientation. And again, look for a strong peak, and here it can be anywhere. And this strong peak corresponds to a dominant orientation of the camera, meaning that the camera is panning or translating sideways. Okay, and so again, the pixels which have this optical flow corresponds to the dominant orientation will be assigned as background, and the other ones will be assigned as foreground. So let's see an example of so there are cases in which we are not able to find dominant motion at most of the frames, or even at all of the frames, and we'll see in a moment some examples of that. So again, what do we do with that? So we just decided to do a very simple thing, and just to resort to appearance-based saliency, meaning frame-by-frame saliency, the classical saliency, and here we use just the method of Margolin et al. So here are, again, examples of initializations. We have two examples here, and we can see that our method automatically decided when to use motion-based saliency and when to use appearance-based saliency. So when it was able to find a dominant motion in many frames, in this sequence of the girl performing the salta, so it resorted to motion-based saliency, and when there was in the sequence of the surfer here, when there was non-rigid motion of the background, it couldn't find the dominant motion in most of the frames, so it resorted to appearance-based saliency. And you can really see how noisy these votes are, and you see that sometimes they miss the girl entirely, and sometimes part of the waves are marked also as foreground, so they're very, very noisy. But what, again, allows us to recover from such a large amount of noise is the fact that we're doing this propagation very non-local, both in space and in time. And this is something you could not have done using local optical flow-based propagation. Okay, so this was our algorithm, and now let's move to the experiment. So we first did the experiment on the SegVec benchmark dataset, which is the current benchmark for unconstrained video segmentation. And we compared ourselves to two strong competitors from the last year. The first is Papazoglou and Ferrari from ICCV13, and the second is Zhang, Javed, and Shah from CVPR13. Again, so there are 12 sequences, and we have frame-by-frame pixel-accurate segmentation, and it's very hard to find today databases which have this accuracy. And here are the results. So we are able to get significant improvement over state of the art, get a very high number in a measure of average segmentation position. So in fact, we got 20% relative improvement over Papazoglou and 40% better than Zhang. Okay? And in runtime, we were also very fast. We were able to perform it in 12 seconds, even less now, and it's competitive with Papazoglou and much faster than Zhang, as you can see here. Now, I want to move you to, I don't want to show you videos from this dataset because it was not that interesting. What I want to show you is experiments on extremely difficult video sequences where we can really see very large differences between our method and others. So let's start again with this example of this girl performing the salta, and this is our result, and you can see that it captures also nicely the hair of the girl, and it deals with the motion blur. Okay, so this was our result, and here again the results of our competitors, and you can see the differences. this was the first example. And here is another. And notice how we are able to capture the athlete even when she was static in the beginning. And this is, again, because we propagated information from far away frames. So this is our result. And here are the results of our competitors. So again, you can see the differences. And here is one last example of the surfer. So again, you can see that we are able to separate between the waves and the surfer, despite the fact that sometimes the surfing board has a very similar color to the waves, but we are still able, because of our very elaborate descriptor, to get the differences. Okay, so in the time I have left, I want to show you several more examples that I've just obtained recently, because we have actually improved the initialization phase. So now we are able to handle much more sophisticated camera motions. So I won't get into details about that, but just to some examples to show you how we can proceed and move to more interesting videos. So here is one example. You can see that we are now able to deal very well with also with zoom or background translation. So this is one example, and here is another. Again, the main difference here is that there is a large amount of frames where there is zoom. And here's one last example. And you can see how low quality these videos really are. But we are still able to handle them quite nicely. Okay. So let's conclude. So I hope that I've been able to show you that using non-local consensus voting of distant co-occurring regions, we can propagate information very far away, both in space and in time. And that we can start from even very noisy initial foreground background votes and still recover the true foreground background segmentation. So our runtime is very fast, and also very importantly, code is online, so you can already use it. And we're able to obtain state-of-the-art results on benchmark data sets and get very encouraging results on new challenging sequences. So thank you for your attention, and as I take your questions, we can enjoy some more videos.